Good afternoon, judges. My name is Charan Bachu, and I'm coming to you from India today. I'm going to try my level best to present, but I hope you don't mind about the difficulties. I'm an incoming freshman at Liberty High School who's passionate about engineering solutions to modern problems. My mention tackles one of, if not the world's largest global issue, climate change. With climate change being such a broad subject, I want to fixate on the SMART component, the gases emitted from smokestacks, specifically capturing all harmful gases, opposed to just carbon. These gases include nearly 45% of total emissions, including nitrous oxide, sulfur dioxide, and of course, carbon dioxide. The exponential rate at which these gases have grown within our atmosphere is unsustainable, which is where my device kicks in. ASCAGE, an acronym for an efficient solution to carbonic acid gas and its environmental desires. I first looked for current methods being developed across the world to improve these surges. Unfortunately, I found that these methods, which consist of carbon capture plants/technologies, have three major limitations: machinery cost, efficiency, and environmental friendliness. Carbon capture plants can cost upwards of $500 million per unit, while others are inefficient, only targeting around 3 to 5% of total emissions and are hardly sustainable. My device, ASCAGE, uses multiple novel technologies, and in doing so, addresses these flaws by being cost-friendly, sufficient, and easy to install in factories and plants. The missions immediately activate the perpendicularly aligned ASCAGE pods via diffusion. Within each pod being this visual, there is certain content of liquid carbon disulfide dispensed in a vapor form initially. Here's a video of me testing with liquid carbon disulfide, and that shows scientific experimentation. I'll be talking to you about the engineering. In each device, there are 8 pods, of which 5 are always activated, with 3 pods on standby. These 3 pods are activated through a temperature-dependent algorithm. In this thermal detection system, a spark from an thermal camera collects thermal and pressure input at the stage of pod 5, the last auto-activated pod, and transmits that thermal input to a TNZ 4.0 microcontroller, which in turn lights up these gaming NeoPixels. The current NeoPixels are only for display. In real life, the system will collect data in 90-second intervals and use C++ code, the very same that we have in elevators. To continue, in each pod I said that there is a certain content of liquid carbon disulfide dispensed in a vapor form. This combines and condenses with the pollutants, thus turning the pollutants to a liquid state themselves. The temperature after condensation at this stage is negative 35 degrees Celsius. These liquids are transported via pipe systems to large industrial refrigerators located around the premise of the plant for 2 possibilities: recycling back into the system for subsequent condensation cycles, or simply the disposal of the excess pollutants. The temperature at this stage, or temperature before being recycled back into the system, is negative 95 degrees Celsius. Up to 30% of my device can be powered by heat flux-based thermoelectric generators, or TEGs, and the remaining is able to be powered through other renewable or green strategies. ASCAGE will drop the cost less than 1% of current methods, being only $475,000 per unit, or to automate an entire factory. My iterations for the device are threefold. First, the subsequent cycles. Second, the thermal detection system. And third, my piston system. Earlier, I talked about how the smoke is recycled and collected and ultimately recycled back into the device. But what about the initial procedures? Since there's no smoke that's been collected thus far, there's also none to be recycled. You see, to kickstart ASCAGE, we need to develop an initial cryogenic liquid. I expected liquid carbon to be finalized because of its efficiency in abundance, compatibility, and boiling temperature. However, due to the honeycomb lattice phenomenon of carbon, I finalized that I'd have to implement another cryogenic liquid. I researched liquid sulfur, liquid nitrogen, liquid hydrogen, and even liquid air, but I found all of them to be ineffective to some extent. At that point, I circled back and wondered if I could use another gas I'd studied a lot, liquid sulfur dioxide. And this was the biggest unexpected outcome of my project. The reaction between liquid carbon and liquid sulfur used carbon disulfide, an endothermic reaction of approximately 50 degrees Celsius, assuring the condensation of any temperature or plume or smoke entering ASCAGE. In addition, within my system, I built a piston to lower atmospheric pressure using the ideal gas formula and Gay-Lussac's law. I've designed the piston to be hollow, doubling as the exit system, and I faced several hurdles in determining the ideal diameter. In addition, at the beginning of my presentation, I've talked about the deployment of additional pods to accommodate for higher temperatures, 3 to be exact. Regarding the activation system of these pods, I actually first believed an app of some sort would be sufficient, where the user would manually enter the temperature, and Bluetooth connection would alert the intelligent support in ASCAGE. However, after understanding that the distance between the user and the device may span several hundred meters in some occasions, I labeled Bluetooth as insufficient, and then moved to a thermal detection system, where I developed 2 prototypical systems before moving on to my final iteration with the TNZ 4.0, as mentioned earlier. This was iterated on the engineering level. After analyzing the current industrial market, I've designed ASKH to function with over 95% of smokestack designs in factories and plants. The industrial market for my device is large and aims to be even larger in the future. A 2019 study stated that over 90% of factory managers and 85% of business owners find interest in going green, if methods fall under 5% of annual revenue. With both sides of the story shining, I believe my device has a great value proposition and is feasible in today's environment. My device ASKH is a CCS, or carbon capture system, that's completely original and targets all harmful gases, not only carbon. Global warming is an issue of today, as is climate change, but ASKH can be the solution of tomorrow. This is my bibliography, this is my logbook, this is some code, and these are my prototypes. I want to thank you guys and have a great day.